This is the third part of acids and bases. In part 3, we're going to take a look at buffers and pH, titration, and titration. I think it's just going to be these two things. Let's take a look at buffers. Now, a buffer is a system that opposes a change in pH. Here we show this is an Alka-Seltzer tablet which contains a buffer, so it won't upset your stomach. So an acid buffer contains a weak acid plus the anion of a weak acid. A basic buffer contains a weak base plus the anion of the weak base. So I'm going to go through one example with you. Here's acetic acid, which I'm going to write as HAC. The Ka for acetic acid is 1.8 times 10 to the negative fifth. Here's my dissociation equation. Now, so I'm starting with 0.1 molar acetic acid. And now what I do is I add acetate ions from like sodium acetate. So its concentration is also 0.1 molar. So in this way, the reaction can go to the right and also go to the left. If I just started with the acetic acid itself, I had very little acetate. And so it couldn't go to the left very well. So it wouldn't really be much of a buffer system. So that's an example here. Here's the weak acid, and here's the anion of the weak acid. We would add that from a salt like sodium acetate. So if we want to find out what the hydrogen ion concentration is, we're going to write an equilibrium expression, and then we're going to plug our values in. Now you notice that we're not going to have x squared this time, because we don't have x times x on the top. We already know what one of them is. Now it's just solve for H positive. Well, these two would cancel out, and so we wind up getting 1.8 times 10 to the negative fifth equals the H positive concentration, and then for the pH would be 4.74. So it's pretty easy to get the pH of a buffer system. Probably even a little bit easier than getting the pH of the weak acid. All right. Now, buffer system. Now what happens if I were to add 0.02 moles of hydrogen ions? Well, that's going to cause a shift in the reaction. So if this goes up, that means that the reaction is going to shift to the left, which means this concentration will go down and this one will go up. So shift to the left. Now why will this one go down? Because if this concentration goes up, more of it will combine with the acetate ions and produce the HAC. So this is going to go down by whatever I added, and this will go up by whatever I added. So that these are my new concentrations after adding the acid to my buffer. Now I plug in my new concentrations and find the H positive, and then I find my pH. So you notice that my pH did go down a little bit. It went from 4.74 to 4.57, but it didn't even go down a whole number. So you can see that the buffer opposes the change. It doesn't stop the change, but it will oppose a change. Now what would happen if we had added a base instead of the hydroxide? Then the shift would have gone in the opposite direction. The HAC would have gone down by whatever we added, and the acetate would go up by whatever we added. So these numbers would be inverse, and then we'd have the pH rising, which is what you would expect. All right, for neutralization reactions, we already saw this earlier today. An acid plus a base yields a salt and water. Here's my example, HCl plus NaOH, NaCl and water. Here's my equation. Here's my net ionic equation. So when I react an acid and a base together like this, I wind up really just reacting my hydrogen ions and my hydroxide ions. So what I'm going to do is use that in a process called titration. So in titration, a solution of known concentration is added to another solution of unknown concentration until a chemical reaction between the two solutions is complete. So usually you're looking for the concentration of an unknown acid or base when you know its volume, or you're looking for, you're asked how many milliliters of an unknown acid or base would be needed to react another solution. So we have a couple terms here. One is the equivalence point, the point at which the reaction is complete. And then we have an indicator, a substance that changes color added near that equivalence point. So indicators are the dyes that will change color as the pH changes. So this is what it looks like here. We have a burette, which is graduated to like 1/10 of a milliliter. And we're going to add our solution here to it. Now in the flask already would have a solution probably of known concentration. So we have one solution already in the flask, and we've got another one to it, and here's our indicator. So we slowly add the base until we get a color change. So this indicator that we're using is a dye called phenolphthalein that is clear in an acid, but it's a little bit maroon in the base. Now once that color is produced and stays, then we stop adding the base. So let's see what it would look like if you could graph out the titration of an acid and a base. Well, if we're reacting a strong acid with a strong base, see in the beginning, you're adding the base to the acid and there's not much change in pH. And then all of a sudden, it goes flying up like that, and then we'll level off as now it's all base. So we want to find out what's the equivalence point. So if you have a strong acid and a strong base, when you finish, you're making a neutral salt, and then the neutral salt won't affect the pH. So we expect the pH to be 7 when you're done. So we would make sure that we used a dye that changed color right around that 7 value. What if we had a weak acid like acetic acid and a strong base? Now we're going to make a salt that has an anion in it that can react with water. So what's going to happen? Because we have acetic acid, the acetate ion will react with water and make the water become a little basic. Now we want the equivalent point. See, it's going to be at a pH of 8.72, so we would use a different dye for this one. So the dyes, we have to pick out a dye that will change pH at whatever range we're looking for. So if we have a weak acid and a strong base, we're going to have a pH above 7. And that's our equations up there. Now the last situation could be a strong acid and a weak base. So a strong acid and a weak base is going to give us an acid salt. That means our pH is going to wind up being below 7. And you see the example here is using hydrochloric acid, a strong acid, and ammonia, a weak base. We wind up making ammonium ions, and the ammonium ions then can react with water and produce hydrogen ions, and thus lowering the pH. So it's important to know what kind of salt are you making, and then you can pick out the appropriate dye then. We're going to take a look at 2 different problems for titrations. So here's the first question. What is the molarity of an acid solution if 35 milliliters of it neutralizes 50 milliliters of 0.25 molar sodium hydroxide? Here's our chemical equation. I'm going to write down the data below the substances. So 0.25 molar sodium hydroxide, 50 mLs, 35 mLs, what's the molarity? First thing I'm going to do is going to find the number of moles of sodium hydroxide. And to do that, I'm going to use the formula molarity times the volume in liters will equal moles. Next step, I'm going to take my answer from step 1, moles of sodium hydroxide, and find the moles of HCl. This is why I need a balanced equation. So you notice that the mole ratio is 1:1. So then I'll get the moles of HCl. And then thirdly, I'm going to find the molarity by taking my answer from step 2 and dividing it by my volume in liters. So I'm going to have to convert my 35 milliliters to liters. I'm going to do it all in a row, so let's see what we get. So I'm starting out with my 0.25 molar sodium hydroxide. That's it here. I want it as moles per liter. Now I'm going to convert my milliliters to liters. That'd be 0.0500 liters. So now you see my liters would cancel out. And then I'm going to put in the mole ratio from the equation. So moles of NaOH cancel out. So right now my answer would be moles of HCl. So 0.25 times 0.05 would give me moles of HCl. And then the last thing is I'm going to divide by the number of liters. And I wind up getting 0.36 moles per liter for my answer. I'm going to look at one more problem where the mole ratio is not 1:1. Now in this situation, we have sodium hydroxide and hydrochloric acid reacting together. We read the problem and put the data below each substance to see what we have. 1.420 molar NaOH, 4.50 molar H2SO4. Here's the volume of it. What's the volume of the NaOH? Okay, so they're going to follow the same 3 steps. Find the moles of H2SO4. Find the moles of sodium hydroxide. See, I need that 2:1 ratio. And 3, find the volume of sodium hydroxide. So to do that, it's going to be moles divided by molarity will equal liters. Now because this is a small volume, I'll probably convert it to milliliters at the end. So I start with my volume. I've already converted my 25 milliliters to liters by moving the decimal point 3 places to the left. I'm going to multiply by the molarity. See, my liters will cancel out. Put that there. So my liters will cancel out. Go to liters. Now this is my mole ratio from the equation. That'll cancel out with moles of sodium hydroxide. And then my last step is going to be taking my moles and dividing it by the molarity, which is really just flipping the molarity upside down. And so you can see then, now my moles of sodium hydroxide will cancel. And I get 0.158 liters, which would be better served to have it as 158 mLs. All right, so that's the last video for acids and bases, and it's probably the shortest of the three.